Good afternoon everyone. Welcome to the class of antenna and wave propagation, and we will continue with the topic that is of fundamental parameters of the antenna. And my name is Mr. Himanshu Nagpal, Assistant Professor in EC Department of AKGEC, Ghaziabad. In the last lecture, we have started the topic that is of fundamental parameters of antenna, or you can say these are these are the parameters on which the antenna features can be determined. And first one is the radiation pattern, radiation intensity, beam area, directivity and resolution, gain, beam width, effective aperture area, antenna temperature and impedance, and there are number of more parameters which we will discuss. And in the last lecture we have discussed the topic that is radiation pattern and the beam width. Now we will continue with the before we start with the topic beam area, we will need to have some knowledge about this topic, that is radian and the steradian. What is the difference between the radian and the steradian? We will discuss about this, and then we will start with the topic that is a beam area. So radian and the steradian. This radian is the unit of the angle, unit of plane angle, means if I say the figure is circle, the angle which is this one, this is defined in terms of this angle is defined in terms of radian, that is a unit. But if I say this is a sphere and the angle which is it making, this one, this is a two-dimensional angle which consists of this angle. This is a solid angle. This angle is known as the solid angle, and this is consists of both angles theta and phi, and the unit of this solid angle is unit of solid angle is described in or is measured in steradian. Clear? So the steradian is mainly used for the unit of the angle which is a steradian, and this is mainly used for the three-dimensional figure, and the radian is the unit of the two-dimensional figure in which the angle that is formed, that is a planar angle. So the measure of the planar angle is the radian. If I say, if I want to define the 1 radian, how can define the 1 radian? That is equal to, we know that the angle is equal to length of arc divided by the radius. So 1 radian will be equal to when the length of arc will become equal to radius and length of arc. Clear? So if I say this is a circle and this is a planar angle, this angle, if you can say any angle, planar angle, plane angle, that is equal to 1 radian when length of arc becomes equal to r, means that is this will become equal to r and this is r. Clear? So then it is known as the 1 radian. So for the steradian, and this steradian is the unit of a solid angle, and 1 steradian, if I say this is a steradian is measured in the form of for the three-dimensional figure, that is sphere example, and 1 steradian is equal to, this is a solid angle, the angle which is making, that is a solid angle, this angle consists of both factors, consist of both theta and phi. Clear? So this is 1 steradian is equal to when it covers a beam area of r square. Clear? When it covers a beam area of r square, then the angle which is making, that is equal to 1 steradian. Clear? So you will see here the area which is equivalent in area, that is equal to r square, and this one is the radius of sphere. Clear? Now see, if I want to say how many steradian is in whole sphere. So you can see that whole sphere, surface area of whole sphere, surface area of sphere is equal to 4 pi r square. If I say one solid angle covers the area of r square, one solid angle, or you can say one steradian covers the area of r square, then to cover the 4 pi r square area, how many steradian will be there? Then 4 pi steradian will be there for the sphere. Clear? So you can see that there are 4 pi steradian in a closed sphere. So this I have already told you. So now next term is the beam area or the beam solid angle. Let's say this is the axis, y axis, x axis, and this one is the z axis. If I say this is the area over which I want to calculate the power which is obtained, or this is a, let's say this is a observation area. Now see, the angle which is it makes with the theta. So it makes with angle that is theta, that is this one. And phi it is making, let's say, take the transformation of this area in this xy plane. So the angle which is makes in the anticlockwise, that is equal to phi, and this angle will be equal to what? D phi, differential element, means differential area. And similarly differential theta will be, that is differential angle, that is d theta. So we will see that this is d theta. So how this will be equal to what? This dimension or this dimension will become equal to what? R into a d theta. How? Because length of arc is equal to radius into a angle between the this, and the angle between the separated by the radius, that is d theta, r into a d theta. And you will see, observe that this area, this line which is equal to this line, this is equal to r into a d phi. Clear? So this line, when it comes to this line and taking the theta, then this comes equal to r into a sine d theta d phi. Clear? So the angle which is it makes, so the area which it covers will be equal to what? The area which it covers, it is equal to what? R into my sine theta d phi. Let's say take this is as a square, as a rectangle, length into breadth, this is r into my sine theta d phi, multiply में r into my d theta. So you will see that this area, this differential area which it covers by this solid angle, and this solid angle consists of both phi and the theta, this covers the area of r square sin theta d theta d phi. Clear? So it covers the area of this one, and the solid angle which it makes at this center, the solid angle which it makes at this center will be equal to what? Solid angle which it makes at this center means, if I say this is a cone, the angle which is at the center makes, that is, it will be equal to sin theta d theta into my d phi. Sin theta d theta into my d phi. Clear? Now see, the differential area that is covered by this angle, that is r square sin theta d theta d phi, and this, if I say this is a solid angle, so that is beam dA will become equal to r square into by d ohm, and this is a solid angle. So solid angle is represented by d ohm, and its unit is steradian. And this is what? This is a beam area, which is, this is a beam area, that is equivalent beam area covered by this solid angle. That means the area which is covered by this, the solid angle, that is a beam area. So we will see here like this one, the area which is it covers by this solid angle, by this angle, that is equal to beam area, and the angle which it makes, let's say this due to the half power point bit, this is a, let's say, a half power points, and this is a half power points. The angle which it makes here, that is a solid angle. So you can say this is a, if I say this is a equivalent solid angle, this one, and this one is the actual beam area, equivalent beam area. Clear? Now next one is the, if I want to define the beam area in terms of the power pattern, so you will see that the beam area, I have already told you, this is a beam area over which the power is associated, over which the power is radiated, maximum power is radiated. So the beam area or the beam solid angle or the of an antenna is given by the integral of the normalized power pattern over a sphere. How much power is normalized power is integrated over this sphere, or which the power is radiated, it is a beam area. So the beam area can be represented as we know that the phi varies from 0 to 2 pi, theta varies from 0 to pi, and this is the normalized power theta phi into my solid angle, and this can also be represented as theta vary from 0 to 2 pi, phi vary from 0 to phi vary from 0 to 2 pi, and theta vary from 0 to pi. Normalized power. Now the solid angle can be also presented as sin theta d theta d phi. Clear? Now if I want to express the beam area in terms of half power points, in terms of half power beam width. So I have already told you that let's say this one is the half power points and this also is the half power points. That means if I say this is a 1 milliwatt So these half power points where the power becomes 0.5 milliwatt and here the power becomes the 0.5 milliwatt. So the angle between these two, that is a half power beamwidth, and this both half power beamwidth consists of both theta and also the phi angle, and it covers the area of what? This is a solid. This can also be termed as a solid angle. Clear? So it covers how many most of the power. If I want to see the how much power is radiated by the antenna, so that power which is calculated by the antenna, means radiated by the antenna, is generally calculated in terms of this one, means the power which covers this half power points, the angles, or you can say it is a actual beam area. So the beam area can also be presented by is equal to half power points in terms of theta multiply में half power points in terms of phi. So the beam area often can be approximately defined in terms of the angle subtended by the half power points of the main lobe, because in the main lobe only maximum power is radiated in two principal planes. So beam area can be written as this one. Next term or next parameter, that is a radiation power density. So radiation power density is defined as the how much power is radiated by the antenna per unit area. Means if I say this is the antenna which is placed and this antenna radiates its energy over the whole area, this one. So how much power is radiated per unit area, means per unit square, per meter square, that defines the radiation power density. So we know that this is a instantaneous pointing vector. This pointing vector is equal to E cross H, where W is the instantaneous pointing vector, A is the instantaneous electric field intensity, H is the instantaneous magnetic field intensity. So the total power crossing a closed surface will be equal to what? If I say antenna is placed here and this antenna radiates its energy in all the direction like this one. So the total power which is radiated by this antenna, the total power which is radiated by the antenna, that is described by the P, and this P will be equal to what? This is power, total power radiated, and this P will be equal to what? If I want to say how much power can be calculated, how much power is radiated by this one, so take the differential area of this one. Let's say take a smaller area, take the smaller area which is defined as a ds. And from this, if I want to calculate how much power is radiated by this area, this is defined by as, you can say, let's say this is a differential area. So how much power is radiated by the whole antenna will be equal to what? How much power density multiply में area, then we can calculate the power radiated or total power radiated, means total power which is radiated, that will be equal to the power density, that is watt per meter square multiply में area, that is in meter square. So if I want to calculate how much power is radiated by this differential area, that will be equal to what? That will be equal to what? power density, let's say power density is defined by W, multiply में area. तो total power radiated by the across the ds area, differential area, will be this one. So the whole power is radiated over the whole sphere, it means over this area, will be equal to what? Will be equal to what? Power radiated overall will be equal to integration of W dot ds, clear? And here if I want to calculate the ds over the whole sphere, that means this S surface area, this surface area consists of what? Theta and the phi component, and theta will vary from what? Theta will vary from 0 to pi and phi will vary from 0 to 2 pi. This will be a total power. So the average power radiated will be equal to this one. So average power, if I want to see the average power radiated, that means the can be written as the 1/2 of real part of E cross H into my ds, that is the average power radiated by the antenna. Now if I want to calculate the total power radiated by the isotropic antenna, means this is an, if I say this is an antenna and it radiates its energy in all the directions with equal intensity, it radiates its energy in all the direction with equal intensity. So you will see that total power radiated will be equal to what? Power density, means that is W multiply में whole of the area, that will be equal to 4 pi r square. So the power that is P radiated will be equal to 4 pi r square into by W naught, that, and this W is equal to the power density, that is watt per meter square. Next term is the radiation intensity. Now what is the difference between in the last topic we have discussed, that is the radiation density, and now the topic is the radiation intensity. So what is the difference between the radiation density and the radiation intensity? That radiation density defines the power radiated per unit area, and this is the intensity, that is the power radiated per unit solid angle. Clear? So the how much power is radiated over a per unit solid angle, that defines the radiation intensity. As we know that the whole sphere consists of what? How many solid angles? 4 pi steradian. Clear? Per unit solid angle means how much power is radiated per unit solid angle, that means that is equal to 1 steradian. So the power radiation intensity is generally radiation intensity is described is noted by this term, that is U. This U will be equal to what? This U will be equal to what? Power radiated divided by per unit solid angle, and how many solid angles are there in there? That is 4 pi. So 1 per unit solid angle will be equal to 4 pi. So U equal to power radiated upon में 4 pi. So if I say if I want to describe this power radiated power in terms of the power density, so you know that the power density, if I say this is a whole sphere, so means this total power radiated can be equal to what? 4 pi r square into by W, and this is a power density I have already described you in this one. So this power radiated can be written as power density, that is W is multiply में 4 pi r square upon में 4 pi. It means that U is equal to the power density, that is W multiply में r square. So U equal to radiation density is equal to r square multiply में power density or radiation density, that is watt per meter square, or we can also say that U is equal to total power radiated divided by 4 pi. So the total, if I want to calculate that how much power is radiated over a whole solid angle, that is equal to, I have already told, that is P radiated is equal to upon में 4 pi is equal to what? Radiation intensity, that is equal to U, or you can say that the total power radiated is will be equal to what? Radiation intensity that is U multiply में 4 pi. Clear? If I say this can also be represented as U into में 4 pi, or you can also say that this one is equal to U into में integration of solid angle, because if I say, so if I say this is a per unit solid angle, is if I say how much power is intensity in this will be equal to what? This will be equal to what? D ohm. So how much power is radiated, that if I say this is dp ohm. So the total power radiated and this will be equal to what? dp ohm will be equal to what? Will be equal to what? U radiation intensity, that is per unit solid angle, multiply में d ohm. And if I want to calculate the overall whole sphere, then power radiated will be equal to what? Integration of dp ohm, and this is equal to integration of what? U into में d ohm. That is, and this d ohm, we know that this d ohm is equal to what? U into में sin theta d theta d phi. So this is equal to U into में sin theta d phi, then radiation intensity, and this will be equal to what? Phi vary from 0 to 2 pi and theta vary from 0 to pi. So this is the total power radiated by integrating the radiation intensity over a whole sphere. If I want to calculate the radiation intensity of an isotropic source, that will be equal to U equal to how many for the isotropic source, how many steradian will be there? 4 pi steradian. So per means that is a 4 pi solid angle, means per unit solid angle, that is equal to radiation intensity, that is equal to P radiated divided the 4 pi. Next term is the beam efficiency. The beam efficiency is the another parameter which defines that how much power is antenna is radiated over one lobe, over the major lobe as compared to the other lobes, or you can say how much beam area is covered in the major lobe as compared to the beam area in the minor lobes. So that defines the beam efficiency, that is the beam efficiency is equal to total that is the ratio consists of, means if I say total beam area, if I say this is a radiation pattern of the antenna, so the total beam area of the antenna, that is equal to beam area by this one, by plus this one, plus this one, plus this one, plus this one, plus this one. So means total beam area consists of what? Main beam area, that is main beam area means major lobe beam area plus में minor lobe beam area. These are the minor lobes. Clear? So the ratio of the main beam area to the total beam area, that defines the beam efficiency. Means beam efficiency is equal to the beam area of major lobe divided by the total beam area, that is minor lobe plus major lobe. that is equal to so the beam efficiency should be higher for a good antenna. So in the today's lecture we have discussed the topic that is a radiance steradian, beam area, beam solid angle, radiation density and the beam efficiency. So here I conclude, here I will finish the lecture, and we will discuss the directive and the gain in the next. So book which I have referred for preparing this slide, that is the Antennas by the J.D. Cross, Antenna Theory, Analysis and Design by the C.A. Balanis, and the Antenna and Wave Propagation by the K.D. Prasad. Thank you.